Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering exothermic and endothermic reactions. So our lesson intention is to compare exothermic and endothermic reactions. The success criteria for this lesson is to analyze changes of energy in substances undergoing an exothermic or an endothermic reaction. Firstly though, let's look at some examples of endothermic reactions. We have an ice pack. When you break it apart, we can see it gets colder, and that's because we're causing a chemical reaction. I think it's ammonium nitrate inside of here, and that absorbs the heat energy from the surroundings, and that's how it becomes solid and cold. You can do the exact same experiment here. You're mixing two salt solutions, or two salts, mix them together, put it on a block of wood. What you can see here on this block of wood is there's a tiny bit of water on the wood. So if I was to draw that out, we have our little block, and then we have sort of a puddle of water on top like so. Now what's actually happening, the reason why we're using this apparatus is because when this beaker undergoes an endothermic reaction, like we said, it gets colder during the endothermic phase. So what actually occurs is this water from a liquid form turns into solid ice. And that's just to prove that by you pulling it up, if it has turned into ice, the ice will stick the beaker and the piece of wood together, as you can see in this diagram here. So that's a nice little demonstration people like to use to represent endothermic reactions. Okay, and so we come to examples of exothermic reactions. The most common one would be a combustion reaction. So if you, in this case, we have a piece of metal, not chemistry reaction, combustion reaction. We have the, combustion of a piece of metal with oxygen, as you can see it occurring there. Another example of an exothermic reaction is your hand warmers. So by crunching the metal salt together, it releases heat energy from that. So there's quite a lot of applications you can see there. A lot of the reaction types that we do see, majority would probably be exothermic, though endothermic does occur quite a bit as well, but more commonly I do believe we see exothermic reactions. So why exactly do we give off heat or do we take away heat? And that all comes down to the idea of energies in chemical substances. So all chemical substances have an internal energy value. We call this enthalpy, represented by capital H. The energy of the chemical substance belongs to two main categories. One, its potential energy, or two, its kinetic energy. Now, if we're talking about potential energy, we're looking at specifically the chemical bonds. So we're looking at the ionic bonds, covalent bonds, metallic bonds. So ionic, covalent, metallic, those are some examples. And obviously we can look into things such as their intramolecular, which we'll talk about a little bit more later on in a different part of this course, and intermolecular. So these are all examples of intramolecular, and then we have intermolecular, which is slightly different. Kinetic energy can be related to the movement of the particle, so it could be just what we call translational kinetic energy, which essentially means the particle moving, directly forwards or backwards. And then we also have energy that's associated with its vibration. Now, if you actually look at this animation here, these are just some of the many types of vibrations molecules and compounds can undergo. You have stretching, you have rocking, you have what we call the scissoring, we have wagging, we have twisting, there's also bending as an example. So there's a lot of other calculations we take into account in terms of the kinetic energy of the molecule or compound. When you add all these factors together, potential and kinetic energies, you get the overall enthalpy of that chemical substance you are looking into. Okay, so now we can actually compare the amount of energy the reactants and the products have in that reaction. Remember, reactants means the ingredients that you have at the start of the reaction. Products represents the substances that you get at the end of a chemical reaction. If it's an endothermic reaction, we can find that the energy of a endothermic reaction, or the reactants, is less than the endothermic product. So it kind of looks like this. Another way you can probably represent it is with this diagram here. So I might just label, this is our starting point. This is the energy of the overall reactants. In order to break the bonds, we need to add in energy. So that gives the chemicals a energy all the way up here. This also so happens to be the activation point. So that's the amount of energy required to cause the breakage to occur. Okay, now some of that energy will end up becoming energy to make the bond, and in that process to make the new bonds, some energy will be released, hence why there is a slight decrease in that energy. If there was no bond making, then you just assume that all that energy is used up, but some energy is released because we make new bonds, and then we get our products over here. Okay, but you can see the product, its overall enthalpy or its overall energy is higher than the reactants because it's taken in more energy to break the bonds than when it was releasing that energy when the bonds formed. So hence why we see sort of this sort of energy diagram like this. It's like half of a profile, side profile of a duck, you could say. With an exothermic reaction, we said heat is released. So what happens is if we look at the reactants, they already have a certain fixed amount of energy. We've added a bit of energy to break the bond. Yes, some was added, but more energy got released when making the bond. And so because it used up more energy to make this bond, overall, more energy got released at the end in the form of heat. In this case, the products, if you see here, has a lower enthalpy than the reactants. Okay, the reason being is because there's an excess amount of energy that got released. This point here, we already said it's the activation energy. Alright, so some energy needed to be given to the reactants in order to break it apart, but more energy was released at the end to give the products, which is also why the products have less energy than the reactants. Alright, so in a way to measure enthalpy changes, and this is how we determine whether or not we get an exothermic or endothermic reaction, we calculate a change in enthalpy, or what we call delta H. So this delta sign here, so it's called delta, it represents change. Greek letter, change in enthalpy. So the amount of heat absorbed per mole of reactant or product when the reaction occurs at constant pressure. You don't really need to remember the entire definition, but you just need to know is delta H will tell you whether or not you get an exothermic or endothermic reaction. To measure delta H, we need to subtract the overall enthalpy of a product by the overall enthalpy of the reactants. Again, you're not expected to do this calculation in year 10. What you need to know more so is what delta H represents, and if you're given a value, can you work out if it's exothermic or endothermic, so stuff like that. Okay, so if it's an exothermic reaction, we expect delta H to be negative, so the reactants will have more energy than the products. Heat released to the surroundings. So here's the other thing. The reason why delta H is negative is because heat is released to the surroundings. The reason why for endothermic reactions delta H is positive is because heat has been added into your system. So released to surroundings, we can also say taken from the reaction, taken from the reaction, which is sometimes also known as the system. The reason why delta H is positive here is because it's absorbed by system. Okay, so delta H bigger than 0 always, delta H smaller than 0 if we're dealing with exothermic reactions. Alright, so another way we can actually write or represent exothermic or endothermic reactions is when we write out a chemical equation. So if we have an exothermic reaction, we will tend to write the energy sign on the product side. Because what this is saying is this is the energy that got released in the chemical reaction, whereas if we're dealing with an endothermic reaction, we tend to write the energy sign on the reactant side. And that's because we're trying to represent this energy got absorbed, like that. Another way you can do it is not write energy at all. So let's just quickly cross this one out. And sometimes what we just write is delta H is negative 0 or negative, so smaller than 0, or delta H is bigger than 0. Obviously, if you have the values, you write the values. If not, you can write this as well to represent the fact that it's exo or endothermic. Alright, so let's have a look at a couple of questions. We want to identify the following 3 scenarios: whether the reactants or products have a higher enthalpy, recall whether the process would be exothermic or endothermic, identify whether the heat would be absorbed from or released to the surroundings. Okay, so let's have a look. So first one, burning kerosene. So if we're burning something, we're actually causing a formation of bonds, and if you've ever burnt something, we would experience a higher temperature. So what's actually happening here in terms of burning kerosene, it is a exothermic reaction. So let's just get that across first. Obviously you don't have to do this in the same order, but there's that. So if it's an exothermic, that means the reactants will have a higher enthalpy than the products. So in this case, that also means that heat is released. Okay, next one we have mixing solid barium hydroxide with sodium thiocyanate. The following reaction takes place and the reaction mixture becomes cold. Okay, so obviously most chemical reactions isn't as simple as one breaking into another or one forming into another thing. Most generally, when you see a chemical reaction, you have 2 things or multiple things come together and you get all these different chemicals that come out. So it's not as clear cut whether or not you have an overall endothermic or exothermic reaction. In order to look at that, you'll need to calculate enthalpy change, or you can also look at the type of temperature change that occurs in the reaction. In this case, because we have a reaction that becomes more cold, we can safely assume it's endothermic, which means that the products have a higher enthalpy, and we can conclude that heat was absorbed. Next one, we have ice melting at 0 degrees Celsius. Now this is an interesting one, more so because with ice, you assume that the reason why it melts is because you're increasing the temperature. Okay, so you might think it's an exothermic reaction. However, this is actually an example of an endothermic reaction. The reason being, if you imagine how water is structured, water is H2O. Now, ice is a solid. Now, the concept of a solid is all these chemicals really densely packed next to each other. Okay? If we melt ice, what we're actually doing is we're trying to break the bonds between each individual water molecule. So what we're actually doing in this melting process, we're actually breaking bonds between H2O molecules. So to break it, we already said we need energy. So all that energy from changing the temperature actually goes into instead breaking the chemical bonds, and so we get the products will have a higher enthalpy because it's an endothermic reaction, and it also means heat has been absorbed. Okay, so that's the explanation why melting water and also evaporating water is an endothermic reaction. If you actually look at the solids, they're quite packed together, whilst the liquids, they get less and less, and then gas less and less. So if we're progressing over on this direction, we are causing an endothermic reaction, right? Because we're adding in energy to try and separate these bonds away from each other. If we were removing energy from the system, then we're getting an exothermic reaction, because we're gonna cause the bonds, might just do it in a different color. So exothermic reaction, we're causing the bonds to come back towards each other. Just keep this in mind next time you look at ice melting or when things boil and evaporate. These processes are actually endothermic reactions. The last thing we need to talk about is how do we know if a chemical reaction will occur? And this comes down to the concept of an energy profile diagram, this one here. So we already said activation energy is the minimum amount that's required to cause a chemical reaction to occur. If we don't have enough, we won't have a chemical reaction occurring. This example here is an endothermic reaction. How do I know? Because I can see that the product has a higher enthalpy than the reactants. Okay, we can see that the very peak of the activation energy, that's called the transition state, and that's where our chemicals will transform from our reactants into our products. And this is being consistent with what we showed before, how the energy profile diagrams of endothermic reaction, the products have more energy, and exothermic reactions where the reactants have more energy. Use the energy diagram. What is the function of the activation energy in a chemical reaction? The activation energy is what we could call the energy barrier that reactants have to have for a successful chemical reaction to occur. For an exothermic reaction, why is the total energy of the product lower than the energy of the reactants? The reason for that is because excess energy from the chemical bond formation is released to the surroundings. That's also to say that the bonds, or our products, have stronger chemical bonds. And so that concludes our lesson for today. Just going through everything we need to know about exothermic, endothermic reactions and activation energy. In the next lesson, we'll talk about reaction rates, but thank you for listening up till now, and I'll see you next time.